Good afternoon. My name is Samantha Riles from Sugar Research Australia, and I'd like to welcome you to our second Milling Regional Research Seminar for 2020. Today we have two speakers. Dr. Darryn Rackemann from Queensland University of Technology will be presenting on investigations to mitigate the effects of juice degradation in factory evaporators on sugar recovery and quality, corrosion and effluent organic loading. Our second speaker is Dr. Changrong Shi from Queensland University of Technology, who will be presenting on assessment of microbial degradation in factory mixed juice and filtrate. Please note that today's webinar is being recorded and a copy of it and the slides will be sent to all registrants. Throughout the presentation, all attendees will be on mute. If you have any technology issues, please send a message in the chat box, which is located on the menu bar of your webinar screen. If you experience any issues in hearing the sound coming from your computer, please feel free to join by phone. I put this number in the chat box. I will be assisting as co-host to ensure all runs smoothly. We encourage you to take an active part in today's webinar by asking questions. As this webinar is in listen-only mode, you can do this at any time throughout the webinar by typing your question into the Q&A button on the menu bar. At the end of each presentation, there will be an opportunity for Darryn and Changrong to answer those questions. If it is easier for you to ask your question verbally than to type in the Q&A, please use the hand up button and then I will be able to unmute your microphone. As I moderate the questions, I will let you know who is asking the question. If you prefer to stay anonymous, there is a box you can check to remain anonymous. Our attendees for today's webinar include staff from these milling companies: Mackay, Sunshine Sugar, Heck Group, Bundaberg Sugar, Wilmar and Tully. I'd now like to hand you over to our first presenter for today, Darryn.
Okay, welcome. Thank you all for joining us today to hear a bit more about the research that we've been undertaking in a couple of projects. Yes, we'd really welcome any feedback, any ideas, any suggestions, but I'll get right into it. So this is the project, Investigations to Mitigate the Effects of Juice Degradation in Factory Evaporators. Mainly looking at sugar recovery, sugar quality, corrosion and effluent organic loading. So as a bit of a background, this project follows on from the Blueprint project, which finished about 4 years ago. That project started to look at some of the effects that occur when factories start to implement steam efficient measures. One of the main things is that the evaporators are run hotter at the front end and a lot more area. And that translates to longer residence time at high temperature, and this causes some sucrose losses. So the Blueprint project found that in some steam efficient factories, the sucrose losses were getting up close to 1% across the evaporation. We also found that 70 to 90% of this loss actually occurred in the first two effects. And this is mainly attributed to the design of Robert type of evaporators. And to put this into context, a sucrose loss of 1% compared to 0.1% in a non-steam efficient factory would lead to around 1.6% less sugar being produced. And this, for a typical factory that might process 1.5 million tonnes of cane, this could be a revenue of around $1 million. Interestingly, a lot of the sucrose loss work that was done in the 90s here in Australia by Peter Wright and a few others sort of found that the sucrose losses was probably highest in the ESJ tanks compared to the evaporator station, mainly because it was the ESJ tank had a holding time of around 30 minutes at that 100 degrees. And so it was only when we re-looked at this issue, when factories have started to implement steam efficient measures, that we've realised that significant losses can occur. So that was pretty surprising initially. This project also found that in steam efficient factories, there was a tendency to have condensates of very low pH as well. And this led to corrosion problems, premature equipment failure, replacing calandrias and piping and valving. And if this wasn't, the organic loading wasn't causing corrosion issues, it could also cause higher organic loading in the injection water circuits. So this project is wanting to look at these kind of effects in a lot more detail. The Blueprint project really only looked at measuring the operating parameters in the evaporators, and looked at the sucrose and sugar levels. Whereas now we want to look in a bit more detail into all the other impurities and what's occurring. So sucrose degradation is a hydrolysis reaction that's largely dependent on pH, temperature, and residence time. So they're the big three operating parameters that influence sugar degradation. And these can be reasonably predicted by correlations such as the one given by Vukov. However, the other degradation reactions are largely unknown. The mechanism of acid formation and how this interacts with sucrose degradation is something we want to understand a lot better. And it's not just acid formation, but it might be protein or polysaccharide degradation that's the instigator of that acid formation. So the Blueprint also confirmed that scaling in the evaporators can help catalyse the reactions, and other researchers also found that fructose and glucose can also catalyse the hydrolysis. But we really want to understand what impact other impurities, whether it's ash, salts, phenolics, or whatever else in the juice, may also be impacting on these degradation reactions, so that we can then look at ways to stop these reactions from occurring. So if we look at the project objectives, yes, we want to determine the effects of sucrose degradation, and we're going to do this through three main objectives. Firstly, we're looking at characterising the juice, condensates and vent streams of evaporators in both high temperature, steam efficient factories, and comparing these with conventional lower temperature, steam efficient factories. We then want to look at determining the degradation reaction pathways that produce acids as well as sucrose loss in evaporation. And we're going to do that in a laboratory evaporator where we can control the conditions much better. Once we understand these degradation reactions, then we want to develop strategies to mitigate these issues. And we also hope to be able to test these in the laboratory evaporator. So today I'll talk a little bit about the laboratory study, as well as some of the factory sampling and measurements. And as you see, the project actually has an embedded PhD within the project, and they're both doing the factory sampling and analysis, as well as the laboratory evaporator work. So moving on to the methodology. So the first part of the project is characterising the various process streams in the evaporators. So like I said before, we're looking at low and high steam efficient factories to see if there's any noticeable differences in both juice composition or what occurs across evaporation. So we're looking at the juices and the syrup at the end of the evaporation to look at the sucrose loss that occurs, and as well as the impurities in those streams. But we've also expanded the program to look at what's occurring further upstream. So we've taken measurement samples from mill juices and the diffuser at Invicta to look at where some of these impurities may be coming from. There is some theories around acetates and potential lignin degradation products that occur across clarification, either or before, where hot water is in contact with the bacillo and bagasse is leaching these impurities into the juice, which then cause problems in the evaporator. So the initial project was going to look at sampling over 2 years in 2017 and 2018. However, we had a slight delay in getting a PhD student into the program. So we split the 2018 season samples across both 2018 and 2019 to allow us to get a little bit more sampling done. So I'm going to talk mostly about the 2018 season samples. We've got a lot of samples there from 2019, but we've yet to analyse them all. We've also took a lot of samples of the noxious gas vent streams and condensates to understand where the impurities or sucrose degradation products are going. So we can look across the evaporator station and understand where both the sucrose as well as the impurities, where they end up. In the blueprint project that was run previously, we've really only looked at the sugar and then and a little bit on the organic acids. But now we want to understand further around some of those other impurities, polysaccharides, phenolics, and proteins. So to run through the sugar factories where we did the sampling program, the two on the left, ISIS and Invicta mills, were selected as examples of low steam efficient factories, typically operating around 50% or thereabouts steam on cane. And the two factories on the right, Pioneer and Condong mills, were examples of steam efficient factories operating with a steam on cane of approximately 40% or a little bit less. Now the main change differences between those factories is obviously the vapour bleeding arrangements, but the other, I guess, aspect is the larger amount of or relative area at the front end of the set, and this also translates to the number one effect operating around 5 to 10 degrees hotter than the non-steam efficient factories, and potentially more than 3 times the residence time at the front of the set. But just to look at some of these results, this is the average of all the tests that were conducted in the 2018 season. So we looked at the sugar and impurity levels in both the mill and diffuser juices at Invicta, as well as the ESJ and the syrup at all these factories. Using the operating parameters at the time, we were able to use the Vukov correlation to predict the sucrose loss, and then we compared that with the measured sucrose loss, which was calculated from the change in glucose percentage fructose from the ESJ to syrup. So what you'll see there is that the two non-steam efficient factories have very low predicted and measured sucrose losses. Measuring sucrose losses when it's close to zero is a little bit hard because of analytical errors. But anyway, so the steam efficient factories had high predicted sucrose losses from the Vukov correlation. Pioneer around 1% and Condong around 1.5%. Now the measured sucrose loss is only around 60% or 60 to 70% of those predicted losses. So what this tells us is that there's either potentially a little problem with the accuracy of our measurements, or the Vukov correlation may not be as accurate as we'd like, and that's something that we want to look at in the laboratory test program to see if we can improve those two measures. The other thing I wanted to show here is just the levels of impurities at the various mills. What we were looking for to see is if some of the steam efficient factories had significant differences in organic acids or phenolics compared to their non-steam efficient counterparts. And what you can see is that there really isn't too many differences between the various factories, and it's likely not caused by the steam efficient measures. There's quite a variation across the various factories. But generally you can see that across evaporation, the polysaccharides and proteins generally reduce as those impurities are actually destroyed during evaporation. And the organic acids and phenolics contents increase across evaporation. So these are likely being produced, sorry, these aren't likely, they are being produced during evaporation. You'll also see that there's a large drop in some of these impurity levels from the milling juices to ESJ, which is likely caused by the clarification process. A bit of more of a summary of those results. The number 1 mill juice contains 50 to 60%, makes up 50 to 60% of the mixed juice and has greater than 2 times the amount of sucrose, but significantly higher fructose and glucose compared to the number 2 mill juice, which the number 2 mill juice has larger amounts of protein, polysaccharides and organic acids. It's probably what we'd expect. The diffuser at Invicta, compared to the number 2 mill juice at Invicta, has lower amounts of polysaccharides. So potentially the hotter conditions that exist in the diffuser may degrade some of those polysaccharides. But at the same time, the level of proteins and organic acids are higher in the diffuser juice, and potentially that hotter conditions may be extracting these impurities more from the fibre and into the juice. Across evaporation, the purity increases slightly at ISIS, and this is caused by those impurities being degraded. But at Condon, the purity decreases across evaporation. This is probably due to the fact that impurities are being produced at a higher amount than the impurities are being destroyed. But generally across evaporation, the organic acids and phenolics, like I mentioned before, increase, and the proteins and the polysaccharides decrease. And we also see a larger pH drop from ESJ to syrup at those steam efficient factories, and the higher sucrose losses at the steam efficient factories. But to look at this sort of more at a broader level, we're looking for trends that may direct where we conduct further research. So we can see that the sucrose loss is largely influenced by the ESJ pH. This top figure in the left. Just apologise, we've actually got a window cleaner here at the moment. We're having problems with sound here. Sorry, and in this bottom left corner, there's a trend showing that the sucrose loss correlates seemingly with the total amount of ESJ impurities. Now, these ESJ impurities are the combined levels of organic acids, polysaccharides, proteins, and phenolics that were measured. And on the right of that screen, we can sort of see there's a correlation between sucrose loss and phenolics and polysaccharides. The red squares and the black crosses. So you can see that there's a positive correlation with increasing sucrose loss with increasing level of those impurities. So that was interesting. I don't think we've even considered phenolics in the past, but it's showing up that it could potentially be one of those interacting factors that or reactions that we're looking for. And there is some literature that both phenolics and polysaccharides will react together and cause some degradation and maybe causing some of those either acid formation or directly contributing to sucrose loss. And the top right chart shows the difference in some of the operating parameters that we sort of should be aware of, and the differences between the steam efficient and non-steam efficient factories. So the non-steam efficient factories are this cluster on the left of the graph. And you see that with increased residence time, with increased temperature, and can't quite see, but I think it might be increased, pH drop, we see a positive correlation with sucrose loss. So those trends gave us something to think about when we start defining the laboratory program. We also looked at some of the condensate analyses. Generally, we found that there was only small amounts of organic acids in the condensate streams. So even though we might have very low pH at some stage, in some condensates, we weren't finding a large amount of organic acids. The predominant component in the condensates was ethanol, and that was highest in the number 2 and number 3 condensates. But we also found significant amounts of methanol in the later condensates, as well as the vent streams. So this methanol is potentially coming from one of the degradation of the impurities. The general comment that we make is that this pH trend in the condensates does not necessarily correlate with the observed sucrose losses. And to demonstrate that, if we look at the Invicta results, we'll see that from the number 1 to the number 5 condensate, there's a large drop in pH, whereas there wasn't a large observed sucrose loss at that factory. ISIS are quite unique in that all their condensates are quite high. So we're not sure exactly what causes that. In the Invicta results, I've highlighted a few data points. So during the 2018 season, I think the number 2 condensate had slightly lower pH than what we expected, and that was potentially due to a leaky tube. So, getting a little bit of sugar into the condensate can cause acids to build up. But generally, by the number 5 condensates, the pH is quite low. I've added a little bit of data here for the 2019 season, and we did a few extra studies at both Invicta and Pioneer. And what we found was that in this middle period for Invicta, where the number 5 condensate gets to below 4, this actually occurred a couple of days after a rain event, and Invicta were processing a lot of stale cane at that point. Interestingly, we went to Pioneer later in that week, and that's the result there where their final condensates got down to below 5. So potentially, those results show the effect of rain. So at Pioneer, which is a steam efficient factory, you see that the pH drops from around or above 9 to just above 6. And this is what I mean by there is some large sucrose losses at Pioneer, but the pH of the final condensate is much higher than Invicta in comparison. And Changrong is, I guess, probably what we'd expect of most steam efficient factories in that that do observe higher sucrose losses, in that the sucrose losses are likely to cause acids to form, and those acids will be boiled off and go into the condensates and eventually lead to low pH, which does occur towards the end of the set at Changrong. So in summary, we've examined a lot of the operating parameters and juice composition. Now this was sort of done for two reasons. One, to understand what's happening and look for differences between both the steam efficient and non-steam efficient factories, but also to provide the composition and conditions for undertaking laboratory study. So we've highlighted a few interactions there that we want to test under more controlled conditions. And that's the phenolics and polysaccharides, which show a positive trend with sucrose loss and potentially that pH drop. Interestingly, the phenolics were present in higher concentration than organic acids. And some of these phenolics, so the phenolics include high molecular weight and low molecular weight phenolics, which can be phenolic acids or can be just phenolic precursors. And some of these phenolic acids are actually more acidic than some of the typical organic acids that we see in the evaporators, acetic acid, formic acid, gluconic acid, etc. We thought we saw more phenolics at convector mill, which could be coming from the diffuser. And these phenolics can be either a degradation product of polysaccharides, sugar, or whatever, or it can come from the actual cane plant. So it potentially is either of lignin origin or a degradation product of the sugar production process. And we know that phenolics contribute to colour when it reacts with polysaccharides. And so that's something that we wanted to look at in a bit more detail in the laboratory work. So to summarise all this, we see a lot of the juice composition on the left-hand side here, and some of the reactions that are occurring. So the sucrose can degrade by microbial or acid catalyzed hydrolysis. Now in the evaporators, it's mainly just the acid catalyzed hydrolysis that leads to sucrose loss, whereas all the other impurities can either cause the formation of acid degradation products, which cause a pH drop of the juice, or can cause acidic condensates. Now the pH drop of the juice then comes back and influences the acid catalyzed hydrolysis reaction, leading to more sucrose loss. And some of the organic acids and minerals contribute to scale, which is also known to catalyze the sucrose loss reaction. So there's a lot of interrelated reactions, and a lot of these are all governed by pH and temperature. The colour reactions, pH and temperature are definitely some of the key variables in those reactions as well. These can potentially have an issue with raw sugar quality. So moving on to the second stage of the project, which is the laboratory studies, which is what the PhD studies concentrating on. So the PhD student started around a year ago and has been using this laboratory boiling apparatus, which you can see on the right, which is at our Banyo industrial facility. She's been using the laboratory rig to develop a boiling test procedure. She first looked at some model compounds, so sucrose, fructose, and glucose, and looked at the effect of different operating conditions. But in a later work, we'll want to look at the effect of other key impurities. So here's a bit more of a schematic of the laboratory rig. It consists of the evaporator, section here. It's heated by silicon oil, which is running through the external jacket, as well as an internal coil. The juice inside the evaporator is kept well mixed by the stirrer, and the vapour transfers up, goes to a condenser where it's condensed and then can either be sampled or sent back to the evaporator. So we can control the process to maintain juice temperature, and we can also vary the temperature of the silicon oil heating medium. Okay, now I have to work out how to get rid of that annotation. Okay, good. So when we looked at developing the boiling process, we noticed that there's a couple of differences between this rig that we need to consider compared to Roberts evaporators. First one is the materials of construction. The rig is completely made out of stainless steel, whereas there is some mild steel in typical factory evaporators. When we start up the rig, we need to get rid of the headspace environment. So there's a lot of air that's in the headspace initially, and we think that this could accelerate some of the oxidizing reactions. The last part is the circulation and operating level. So in this rig, we have been operating it with the coil completely wetted, and we've been operating with forced circulation. Whereas in Roberts vessels, they typically operate with 35 to 45% up the tubes, and you're getting a lot of natural circulation to keep everything well mixed. The heat transfer is also a little bit limited in the laboratory because we're using silicon oil, which transfers heat by conduction compared to the condensation or latent heat transfer that occurs in sugar factories. And this basically leads to lower boiling intensity in our laboratory rig, and we've tried to mitigate that by including the forced circulation to keep everything well mixed. Okay, so looking at some of the results from the laboratory rig, we boiled both factory ESJ as well as synthetic juices. And what we found is that the factory ESJ exhibit a lot lower sucrose loss over time. So in these conditions, the juice was boiled at around 119 degrees. And what we found is that during the heat up period, which typically took 20 to 30 minutes, a small amount of degradation occurred. And we'll see that in these three graphs. So the bottom graph shows the change in pH. So as the pH starts off as alkaline, but after the heat up period, the synthetic juices are slowly becoming more and more acidic at a much greater rate than the factory juices. And we see this also in the variation in the colour formation. So a large amount of colour formation occurs during this heat up period. Now we've attributed a lot of this to the alkaline degradation of the fructose and glucose. So that's why you see a lot more colour being formed during this heat up period while the juice conditions are alkaline. And then lower amounts of colour formation, even though we're seeing much higher levels of sucrose loss towards 60 minutes of boiling. So a lot more colour formation was occurring with the factory ESJ, and that was mostly because the pH stayed alkaline for a lot longer. But as the sucrose loss occurred, we saw the pH slowly reducing as the sucrose degraded to organic acids. But another important thing that we found was that the buffering actions of the salts of weak organic acids that was in the ESJ also helped maintain the pH of the juice. So we were able to confirm that by examining synthetic juice with and without organic acids. So if you have a look at this plot here, you can see that the synthetic juice with organic acids, which is this the two blue lines, the solution pH reduces much less than the synthetic juice solution without organic acids, and the corresponding sucrose loss is much less as well. So that was an interesting sort of outcome that we've seen in this preliminary work at using this laboratory rig. The other impact that we looked at in the laboratory rig was the effect of heating surface temperature. Now, one of the reasons for this is when we first started boiling the juice, what we found is that we needed around 15 to 20 degrees temperature difference between the oil and the bulk juice inside the evaporator. Now this is probably maybe double the temperature difference to what you sort of see in the first effect, where there's only 5 to 10 degrees difference between the steam and the juice inside the first effect. So we were able to increase the heating surface temperature, or that temperature difference between the silicon oil in the coil and the heating jacket and the juice that was boiled inside the vessel. So we've looked at between 18, 19 degrees and 29 degrees, but what we found was that it didn't really have much impact at all on sucrose loss or the pH change in the juice or the colour formation. And we're attributing this to potentially that the forced circulation, the mixer that we've got inside the vessel, keeping everything very uniform. So we're not seeing very large or any hot spots where the juice temperature gets too much higher, where kinetically it would then degrade more or cause more sucrose loss. So we will go back and do some more work here by looking at either turning the stirrer off to see if we had that same impact, or running the juice level down to sort of see if some of the heating surface is not fully wetted, whether that will have an impact on these sucrose loss, colour and pH. And this is important because a lot of sugar factories potentially have a little bit of superheat in the LP steam going to their first effect, and we wanted to understand if that contributed to higher sucrose loss or potentially more colour forming in the juice. But so far, we haven't sort of seen too much to indicate that is the case. So that was the preliminary laboratory work. Once we get a better understanding and look at it in a lot more detail, we'll then want to start developing and testing mitigation strategies that should be able to reduce the sucrose loss that occurs in evaporation. So this could be either preventative, by trying to inhibit the sucrose loss and acid formation, or by removing some of the impurities before it gets into the evaporators to sort of see if that allows us to reduce the degradation reactions that are occurring. Or this might be post-treatment, so how can we remove the acidic compounds after they're formed to ensure that they don't contribute to further sucrose losses. So that's the next phase that we'll be looking at in the project. The blueprint project did find that the process control, by optimising the operating parameters, can allow you to reduce the sucrose loss to some extent. So optimising the pH is the key operating parameter that we can sort of control. But engineering designs are another measure. The Roberts evaporator has a large juice volume, and some of these new evaporators, Kessner's and foil film evaporators, or even Roberts evaporators with smaller diameter and longer tubes, may reduce that juice volume and allow sucrose losses to be reduced. So lastly, I'd just like to acknowledge the project funding from Sugar Research Australia. PhD student, has done a really good job, I believe, Shilani. She was due to present at the ASSET some of the findings of the laboratory study, which will now be delayed till next year. So hopefully you'll all get to meet her and listen to the work that she's been doing. I'd also like to acknowledge the sugar factories and the QUT staff that also helped in the project. So that concludes my talk. So Samantha, do you want?
Yes, thanks, Darren. So if you have any questions, please put them into the Q&A. Now, Darren, we've had a question here from Brian Laverick. How did you preserve the juice samples, and did this impact on the results in any way?
Okay, yes. When we when we sampled the juices, we generally ran them through a cooling coil to get them to around room temperature. We sampled them into a container that had a small amount of sodium azide as a preservative, and then we put that sample into onto ice to keep it cold and to reduce any kinetic reactions to very low. Now, adding sodium azide into the juice solution, I think it was around 0.1 grams in around 100 grams of juice. And that generally lowered the pH by about 0.2 or 0.3 units. But otherwise, I think that was the only impact we saw on the results.
Thanks, Darryn. Another question from Brian. Do you have any theories why the pH of the condensate decreases in number 2 effect, but increases in the number 3 effect, and then decreases again in number 4 and number 5 effects?
Yes, sure. We do have a theory. We believe this could be due to the protein degradation, which potentially produces ammonia, which will then lead to an increase in pH after it's volatilized. So we potentially don't see that occurring to the midway along the step. So in the first reduction in pH is likely caused by the volatilization of acids initially, especially when we consider that a lot of the degradation occurs in the first effect. So we're probably seeing that contributing to the number 2 condensate seeing a reduction in pH. And then as proteins are maybe more slowly degraded and producing ammonia, which helps raise the pH back up. And once proteins are, I guess, as destroyed as much as they are across the evaporators, then we're probably seeing more acids being formed again. And towards the later end of the set, as the Brix increases, it also allows some of these acids to volatilize more readily. And that's why we see the pH reduced towards the end of the set.
Thank you, Darryn. Okay, so that's our questions for the first session, and we'll now hand over to Changrong, who will be presenting second. Thank you.
Okay.
Good afternoon, everyone. Can I start now?
Yes, Changrong, you're right to start. Thanks.
Okay. Today, I'd like to talk about the sucrose degradation as well. But my project is mainly focused on the microbial degradation of sugarcane juice prior to the evaporation stage. The title of my talk today is Assessment of Microbial Degradation in Factory Mixed Juice and Filtrates. As we know that the undetermined sucrose loss has long been a common problem for the sugar industry. And there are 3 main pathways that can result in the undetermined sucrose loss. Those are microbial, enzymatic, and chemical reactions. And results of the effects of these 3 processes on mixed juice has indicated that 93% of the sucrose loss are caused by the microbial activity, while 5.7 and 1.3% of the sucrose loss are arising from the enzymatic and chemical processes. The results indicated that microbial degradation is the dominant contributor to the sucrose loss in mixed juice. In addition to the reduced sucrose content, the microbial degradation also can cause another problems associated with the metabolic products produced. These metabolic products can have a negative impact on the consequent evaporation and crystallization processes, and also have negative impact on the molasses exhaustion. And also we know that the microorganisms cannot be avoided because it comes into the factory associated with the sugarcane itself, and also the delayed cut to crush time, as well as the inefficient hygiene practice can also make it worse. The latest research work concerning the Australian sugar mill sanitation was conducted by Tilbury in 1977. Since then, little work has been done to determine the extent of the sucrose loss caused by the microorganisms. Thus, the contribution of the microbial degradation to the undetermined sucrose loss are still unknown. In the current project, we have 3 main objectives. The first one is to conduct the deterioration test with the 2 typical juice streams from sugar factory. Those are mixed juice and filtrates. And also based on the metabolic products concentration over time, we did a prediction of sucrose loss based on specific metabolic products. Those are mannitol, polysaccharides, and lactic acid. After that, we did an evaluation of the beneficial of using biocides in reducing the sucrose loss and also the formation of metabolic products. Before we conducting the degradation tests, we did a compositional analysis for the 2 juice streams. We found that 3 kinds of typical metabolic products, polysaccharides, lactic acid, and acetic acid, the concentration were higher in filtrate compared to those in mixed juice, which is indicative of the occurrence of microbial degradation in the processes between mixed juice to filtrates. And after the compositional analysis of the juices, we conducted the degradation tests in our laboratory at ambient temperature. And during the degradation processes, the subsamples were withdrawn from the system according to a specific time frame. And for the analysis for bricks, pH, sugars content, and organic acids content, polysaccharides content, 1-kestones and mannitol concentration as well. Based on the variation of these kinds of metabolic products concentration, we established the mathematical relationship between sucrose loss and the metabolic products. These allowing for the sucrose loss to be predicted based on specific metabolic products. This is the result of the bricks and pH throughout the degradation process. The right one represents for the bricks, and the left one, the left one is the bricks result, and the right one is the pH result. We can see from the purple curve, which represents for filtrates, we found that at the initial stage, both bricks and pH value stays relatively stable compared with that in mixed juice. As we can see a sharp decreasing in the initial stage in mixed juice for both bricks and pH, especially the pH value showed a sharp decreasing at the first 8 hours. This is the result of sugars, mannitol, and 1-kestones concentration throughout the degradation process. The sugars including sucrose, glucose, and fructose. The left graph is the result of those compounds in mixed juice. The right one is those in filtrates. We found that glucose, fructose, and 1-castose had a similar tendency throughout the process, which increase at the initial stage and arrive at the maximum value, followed by a decreasing trend to a relatively stable level. And also, the tendency in mixed juice are similar to that in filtrates, while the sucrose concentration decreased all the time till the minimum value, which is 0. While the mannitol concentration in both mixed juice and filtrate increased throughout the degradation process. And also we found that these 4 degradation products, mannitol, fructose, 1-castose, and glucose, the concentration were higher in mixed juice than those in filtrates. This is the result of the organic acids. Among the 11 kinds of organic acid, we find 6 typical organic acids experienced significant variations throughout the process. Also, we can see from the 2 graphs that the lactic acid has the highest concentration among those detected organic acids, followed by acetic acid, succinic acid, and digluconic acid. These 4 typical kinds of organic acid experienced increased intent throughout the process, while citric acid and transaminatic acid experienced significant variation as well, but the tendency throughout the process is decreasing. Based on the single organic acid concentration, we calculated the total organic acid, and we found that in both mixed juice and filtrate, the total organic acid concentration has a similar tendency as well. In the first 24 hours, the concentration kept stable. From 24 to 72 hours, there is a sharp increasing. After that, it's kept at a relatively stable value. And also we found that the organic acid concentration in mixed juice are higher than those in filtrate as well. For including those metabolic products, 1-castose, mannitol, and reducing sugars, we found that these metabolic products has a higher concentration in mixed juice than filtrates. This could be due to the a lower initial juice pH for mixed juice, and also the mild condition for microorganisms thrive, as the filtrates had experienced a very high temperature at the clarification stage. We also analyzed the polysaccharides concentration, as we know that at the initial stage, the concentration were higher than that in mixed juice. But throughout the degradation process, we also found that there is a significant variation between the concentration in filtrate and mixed juice. We can say that the probably leakage of the polysaccharide from the mud in the filtration stage could partially contribute to the initial polysaccharide concentration. But throughout the degradation process, the significant high concentration of polysaccharides is due to the microorganisms activity. Other than the Leonel cornerstock, mannitol, this is a kind of bacteria which produces the dextran. We also analyzed the alcohol content throughout the degradation process. we found that no ethanol was detected in both mixed juice and filtrate samples. However, a reasonable amount of methanol were produced in both juice samples. But the concentration fluctuated throughout the process. This could be due to the volatility of methanol, as it boils at 65 degrees. And also the formation of methanol could be due to the existence of pectin in cane juice, as it has been reported that methanol has been the metabolic products of yeast fermentation of pectin. Based on the results of the degradation process, we get into conclusion that sucrose loss occurs in the processes between mixed juice and filtrates by the activity of microorganisms. And there is a linear relationship between the mannitol concentration and time, polysaccharide concentration and time, and also lactic acid concentration and time. And according to these relationships, we establish the mathematical relationship between sucrose loss and metabolic products. We found that there is a linear relationship between the sucrose loss and mannitol concentration, while the relationship between sucrose loss and polysaccharides or lactic acid are nonlinear. Based on the established three mathematical relationship we did a prediction of the sucrose loss in mixed juice and filtrate for 1 hour, which is a typical residence time of sugarcane juice in Australian sugar mill. When mannitol was used as the indicator, the sucrose loss in mixed juice was estimated to be 0.062%, while that in filtrate was negative. It implies that the mannitol could be not prop for the prediction of sucrose loss in filtrates. When polysaccharides were used as the indicator, the estimated sucrose loss in mixed juice was 0.296%, while that in filtrate was 0.898%, which is higher than using mannitol as indicator. We also found that lactic acid was a poor indicator for sucrose loss. In summary, we get to know that recycling of filtrate to mixed juice contributes not only to the sucrose loss, but also have a negative impact on the overall sugar manufacturing process due to the significant contribution of metabolic polysaccharides. And also we suggest that both laboratory and factory trials should be conducted with the use of biocides in milling and filtration stage of Australian sugar mills. And based on the outcomes of these projects, we proposed a small milling research project proposal, which have two main objectives. The first one is to identify the microbial contamination sources within the sugar mill juice streams. The other one is to demonstrate the efficacy of FDA-approved biocides in reducing microbial sucrose loss. And this proposal has been submitted. Probably we can get the result in the end of April. Being working with this project, we acknowledge the support from SRI and QUT for the project funding. And also we thank to the assistance of CAF staff in QUT for helping analyze the metal ions concentration. These are all the contents that I'd like to report today. Thanks for your time.
Thanks very much, Changrong.
No worries.
Okay. I'll just give a couple of seconds for any questions to filter into the Q&A box. Please feel free to ask any questions for Changrong or for Darryn, if you've thought up anything more for Darryn. Okay, I'll just do my conclusion, and if any questions come in the meantime, I'll go back to them. So thank you for attending our second SRA Milling Regional Research Seminar. We hope that you found it of value and are keen to get feedback from you. After this session, you will receive a link to a survey that we'd like you to complete. It will only take a few minutes of your time and will allow us to improve our webinars in the future. Tomorrow you will receive an email with the recording and the slides. Our next Milling Regional Research Seminar will be held on the 22nd of April and will be presented by Professor Ross Broadfoot on pan design and operational changes to suit Australian pan stages operating on low pressure vapour. Our second presenter is Dr. Ayman Ashtani, who will present on performance of the SRI fixed element cooling crystallizer at Broadwater Mill. All of these topics and recordings from previous webinars are available on the SRA webpage. So I'm just checking on the Q&A now. There's nothing more that's come in. So if everybody is happy, you'll also receive Changrong and Darryn's contact details on the email that you get tomorrow that includes the slides and the recording. So feel free to reach out to them if you have any questions. Thank you all for coming along today, and we'll see you at the next webinar. Thanks so much.
Thank you. Stop.